So the gradient of this function will be perpendicular, will be normal to the surface we're actually looking to find a tangent plane for. So take your gradient. Since capital F, my hyperdimensional version of this function, since it's a function of 3 variables, it'll have a 3-component gradient. And I'll need a 3-component normal vector to deal with a 3-dimensional football's tangent plane. Okay? So building my gradient, the partial here with respect to x, you really just go one term at a time. 2x is my I component for gradient, 6y will be my j component for gradient, and 8z is my k component. So then evaluate this. At the point given in the problem, I'm looking to find the equation of the tangent plane to this, football at that point on its surface. So I want to evaluate the specific gradient at 2, 2, 1. Remember, that's x, y, and z in alphabetical order. So my hyperdimensionalized gradient, or 2, 2, 1 plugged in for x, y, z, will give me a perpendicular normal vector. 2 times 2, 4 for I, 6 times y, so 6 times 2 is 12 for j, and 8 times 1 will keep 8 for k. So this is guaranteed to be a normal vector to the surface of that ellipsoid, that football. And the two things you need to get your tangent plane, or to get any plane, doesn't have to be touted as a tangent plane, but you just need a normal vector. So yay, and you need a point of tangency. And that's the point that's given in the problem. And then you go refer to what I got on the board to your left over there. To find the equation of a plane, you use the normal vector as the coefficients of x, y, and z, and then you plug in the point to get the actual constant value that goes on the right-hand side. What I usually do is, once we do a few examples with the 4 times x minus 2 quantity and then plus 12 times y like that, what I do is go in and take for granted these are your x, y, z coefficients in order. The tangent plane is going to be 4x plus 12y plus 8z. But then your constant comes from evaluating this by using 2 for x, 2 for y, and 1 for z. So then the right-hand side would be 4 times 2 plus 12 times 2 plus 8 times 1, because you want to guarantee not only is that a point on the sphere, but since this is the tangent plane at the point of tangency, the plane has to also carry that point. So that's why plugging the point into the equation tells you the constant that goes on the right-hand side. So then, if that's too loopy for you, feel free to go back, the way you did on test 1. It still gives you the same thing. It eventually turns into this calculation. I'm just taking for granted that the normal vector's coefficients or components are always your x, y, z coefficients every single time. So let's see what this constant is on the right-hand side. 8 plus 24, so that gives me 32, plus 8 more, it's going to give me 40. So you state this as your answer. You're obviously a very studious person, so you check the back of the book, you check Bob, back of the book, to see if you get the right answer. And then when you check the back of the book, you see that, are you disappointed?
No.
No, because in most cases, the answers are usually kind of reduced to lowest terms. So if you divide both sides of this equation by 4, it's still the same plane. It's still the same equation. Now this we can visualize, if you want to see it. Let's graph our football and overlap it with the graph of our tangent plane, just to see if I'm just giving you a big crock of nothing. So I'm going to toggle to the PC. There we go, toggle. So our ellipsoid is generated by, let me make it kind of a frosty gray color. The ellipsoid was x squared plus 3y squared, and then plus 4z squared.
Evaluate it.
and then equals 20. So again, you're dealing with a rectangular domain. Your x, y, z values are sort of invisibly slicing into this. -2 to 2 for x, -2 to 2 for y, -2 to 2 for z. So anything outside of that box is invisible. So it's kind of cool when you see it like that. But let me zoom out a little bit so we can make our box, our domain for this picture a little bit bigger. Okay, so there's, okay, close. Almost there. There's a little bit on the x-axis that we're missing. So it kind of looks like an olive. But okay, there we go. Make the resolution a little higher so you get rid of some of those kinks in the graph. So that's what our football looks like. Okay, it looks more like a pill or something like that. But anyway, it's an ellipsoid. Now if I overlap it with the graph of our plane that we just found, and I'm going to just go for the simplest equation. So let me do a new equation. The plane we got was x plus 3y plus 2z equals 10. Oh, hello, 10. And maybe graph that in the same color. All right, let's make it mauve. All right, so now it's completely, obscuring our ellipsoid, but if you rotate it a little bit, and then, bam, stop. Does that look tangential to you?
Yeah.
Yeah, I was trying to get it right there at the point of tangency, but yeah, you can sort of see how the plane is just sort of touching the edge of that ellipse. So I'm giving you good information. This is all good stuff. Now, if I wanted to sort of give you a representation of that gradient vector, I can draw, switch out again, I can draw this gradient vector, but I only want to draw the specific gradient vector we have at the point 2, 2, 1. I want to graph this one right here and overlap it with our image. What I really need to do is I want to graph that as a parametric line in space. Okay? So the equation of a line needs a point, so that'd be the point of tangency, and it needs a direction vector, which would be my gradient. So if I let this be the constant terms in my parametric equations, that will be my t coefficients in the parametric equations. So let me overlap those together. Okay, to graph a parametric curve, I've got to do, I think I showed all this on Tuesday, I've got to do a 3 vector for 3 different equations. So my x equation, the x coordinate of tangency is 2. The I component of the gradient is 4i. So 2 plus 4t would be the x equation for the parametric line I'm looking for. The y point of tangency is 2. The j component of the gradient is 12, so that'd be plus 12t. The z coordinate of tangency is 1. The k component of the gradient is 8, so it'd be plus 8t. And then if I graph this, keep your fingers crossed, there you go. You can kind of see that purple vector. Well, let me make it something you might be able to see a little better. Make it yellow. So does it look like that vector or that line is normal to the surface of that plane?
Mm-hmm.
Yeah, it looks like it's meeting it perpendicularly, at a right angle. And it's also leaving the sphere, the ellipsoid, perpendicularly at that surface. So since it's perpendicular to the tangent plane, it's also perpendicular to that specific slope on the edge of the M&M, or the pill, or the football, whatever you're going to call it. Okay. So by hyperdimensionalizing, by taking this thing, this gray object here, and its 3D equation, and then taking it 1 dimension higher and turning it into a function of 3 variables, this now becomes a level surface of that function. And that the gradient of this function, all the gradients here are guaranteed to be perpendicular to all its level curves. And I just need 1 perpendicular vector. So that's why you needed to have the point of tangency, so you can plug it into that hyperdimensional gradient, and then it turns out to be normal or perpendicular to that level surface at that point. Okay. In my opinion, a much easier way of finding tangent plane equations. It's your first time seeing it, and it may scare the crap out of you, but it's a really systematic way of finding tangent plane equations. Here's the cool thing, it works for lines as well. If you start with a curve in 2 dimensions, and you hyperdimensionalize it to 3D, the gradients here would produce normal vectors to that curve in 2D. Okay? It works for any dimension going 1 dimension higher. Those gradients are always going to be perpendicular to the level curves of that object. Okay? I love this stuff. Okay.
I can tell.
But it's understandable, it's manageable. we've got a little over half an hour left in class. According to the calendar, we need to at least introduce you to section 14.6. Much easier section. There's two things you got to do in this section. You learn the multivariable version of the chain rule. Okay, so I'm starting my numbering back at 1. So this will be a separate link. The first stuff that we did, finishing section 14.5, will be one link for the gradient information, and then I'll start a new link on your D2L page for test 3 stuff for this section 14.6 that goes over chain rule. Okay, the way it works, this is sort of weird to see. The chain rule you've used up to this point has been, something like y equals cosine of x squared minus 1, okay? You have an outer function, you have an inner function, and then you kind of differentiate it by going outer function's derivative first times inner function derivative last, okay? This is the multivariable version of that, all right? It looks kind of scary, but let me go over the rudiments of how it works, okay? You've got a parent function here. Z is a function of x and y. So, in my example here, Z is a function of 2 variables. Z could be a function of 3, 4, 5, 6, any number of variables. But the reason the chain rule is needed here is because there's this sort of cascade of dependency that starts from this parent function. So Z, in this example, is just a function of 2 variables, okay? X and y. Then individually, x and y are also functions of other variables. So for example, maybe Z measures, to kind of go with the example of something you've seen on the test 2 review, maybe Z measures wave height as a function of wind speed and of time duration during the day. Well, then maybe wind speed is also a factor of, local temperature. That could be one of the things that could depend on the latitude, longitude, location on the surface of the Earth. So maybe wind speed itself could be dependent on other things as part of being plugged into this calculation. So, you could have a whole cascade of dependency leading to, the parent being Z. Z depends on x and y like this, and then maybe individually x and y depend on other variables. So the branches could get pretty hairy. Z could depend on 2 variables, 3 variables, 6 variables, and then each of those could depend on 2, 3, 6, and just really have this big, branching set of trees coming down to represent this whole chain of dependency. So what you ultimately want to find out is if the wave height depends on wind speed and wind speed depends on barometric pressure, what is the rate of change of wave height with respect to barometric pressure? You can ultimately get the rate of change of this with respect to not only these two using regular partial derivatives, but you can also get the rate of change of this with respect to any of these guys down here by using the multivariable chain rule, okay? Now here's the way it works. You've got to have a diagram like this. You're going to be given the parent, I keep calling it the parent function. The parent function like this guy right here. And it'll depend on 2 or 3 variables. So it's essential to kind of draw that little branch of dependency. Z depends on x and y, okay? And then individually, like in this case, x is a function of s and t, y is a function of s and t, so you can draw a couple of more branches coming off of them. And then heaven forbid, if s and t were functions of things, it would keep going down and down and down. But as long as you can create this branch network, this is probably the most straightforward way of doing the multivariable chain rule. What you're going to be prompted for, like I said, doing the derivative of z with respect to x and y, that's section 14.3. That's just a regular partial derivative. But if you want to talk about the rate of change of z with respect to s, this s and that s, you have to do this. Do a diagram like this. So for example, if I wanted to get the rate of change of z with respect to s, what I've got to do is link z with every s in the most direct route, okay? Every one of these branches that you see here represent partial derivatives. For example, right here, this branch that links z to x, this is the partial of z with respect to x. This branch that links z to y is also a partial derivative. This is the partial of z with respect to y, okay? And then the branches that stem from x going down to s and t, they are also partial derivatives. From x to s, this is the partial of x with respect to s. This link from x to t is the partial of x with respect to t. And similarly over here, this is the partial of y with respect to s. And this branch linking y with t is the partial of y with respect to t. So in other words, every link in the network that takes you from one tier to the next is the partial of that variable with respect to the one it's going to. Okay? Partial of z with respect to y, and then here the partial of y with respect to s. So if you're prompted to link the rate of change of the parent variable up here with respect to any of these second generation variables down there, let me show you what you have to do. To get the partial of z with respect to s, you want to go from z to each s one at a time. So you'd have this link first, the partial of z with respect to x, and then times the partial of x with respect to s. So in other words, you need to multiply these two branches together to link z, ultimately depending on s. But you're not done. Once you've done that branch, you have to add any other branches that connect z to s. There's one more link that takes you from z to this other s. So there's this part of the chain rule plus this part of the chain rule you need right here. So you start over at the top, partial of z with respect to y times the partial of y with respect to s. And so that calculation, that pair of products, links every z to every s, representing its total chain rule net rate of change, or instantaneous rate of change, technically. It is a derivative we're talking about. Okay?
It's not bad.
It's not too bad. But do you see why this diagram is really essential? You got to have a diagram like that so you can see who's the parent, what its kids are, and what its kids are. So you can link them all together from beginning to end. So in other words, to find out z with respect to s, you're going to have as many links here as you have s's at the bottom of the tree. Same thing with partial of z with respect to t. You want to do the same thing. To connect every z with a t, you'll start with partial of z with respect to s, or correction, with respect to x, times the partial of x with respect to t. So in other words, this branch times that branch. And then start over, because now I have to link another z with another t. Partial of z with respect to y times partial of y with respect to t. And that, my friends, is the chain rule, the multivariable version of the chain rule. And I've given you one particular instance. Keep in mind, your parent variable here is just a function of 2. It could be a function of 3, it could be a function of 4. And then those 2, 3, or 4 could be functions of 8, 20, or some heinous mess. So you could have a lot more than just these pairs, you know. For every single link you've got, that's essentially going to tell you how many total things you need to connect together. Sorry. But I don't think it's too terribly bad. Your homework's pretty straightforward. It sort of sticks to, you know, like this. I think I've actually picked 2 of these examples from your textbook. So here's an idea of how this chain rule works. You're given a function of 2 variables. F of xy equals xy plus y squared minus 2x. So that's the parent function. And keep in mind, this symbol here is synonymous with whom? Z. So if that's not called z in the problem, you're welcome to call it z so you can kind of start, or you can just let that be the start of your chain rule tree. Just the symbol f of xy. So f depends on x and y, and then separately, x and y have these dependencies on the variables s and t. X equals s squared plus 4t, and also y is calculated as 12st squared. Okay. So what I want us to do is evaluate a couple of the chain rule derivatives. Let me draw. I didn't really give myself room to draw the picture here. Let me make it really small because I want to at least scan this in. So I'm going to say f is the parent, and f depends on x and y. So it's pretty much the same picture as the previous page. And then x and y separately depend on s and t. So I see exactly how many branches I have to go down to get each of these 2 chain rules that I'm prompted for. I've got this one here, the partial of f with respect to s, and then later on I prompt you for the partial of f with respect to t, bottom of the page. Okay? So let's get started. Let me go ahead and just write out the raw calculation. To connect f with s, I need the partial of f with respect to x first, just going in alphabetical order. And then x is partial with respect to s, multiplied by that. And then I need to start a new branch, the partial of f with respect to y times the partial of y with respect to s. So then, hopefully, like you'd speculate, you go back to your formulas at the top of the page and just fill these in one at a time. Keep in mind it's a pair of products and then plus another pair that's in a product. So, partial of f with respect to x, go back to the f definition, and f's partial with respect to x gives me y minus 2x, or y minus 2, I'll get it right eventually. So everybody see where I got that from, y minus 2. Partial of f with respect to x. And then times partial of x with respect to s, for some reason I switched back to black. That's going to give me times 2s. And that completes that first part of it. And then plus the partial of f with respect to y, so start with a fresh copy of your f. Its partial with y would be x plus 2y times the partial of y with respect to s, which is, that s is linear, so that means it should become 12t squared. Now here's where I may differ than some other teachers, okay? Other teachers are going to want your partial of f with respect to s, bless you, to ultimately be only a function of s's and t's. Which means, after doing this initial chain rule step, you have to go back and replace every y with 12st squared, and replace every x with s squared plus 4t. I'm not going to make you do that. Well, because of this. This is a sufficiently fine answer right here. Partial of f with respect to s. Because you may be asked to do this. Evaluate this for s equals 1 and t equals negative 1. In other words, what would the rate of change of f be with respect to s if those were my s and t values? Okay. So luckily, I've got t's and s's literally in this mix. So I know this is going to become 2 times 1, and that's going to become 12 times negative 1 squared. So I know these values. But where am I going to get these values? Yeah, you got to go back a step. So that's the trade-off. If you don't completely write this in terms of s's and t's, you have to go back to your x, y functions, determine what x and y's values are based on this, and then you have everything you need to plug in. So before you do the plug and chug, go ahead and double check this. If I use those values of s and t, go and pair them with your values of x and y so you can evaluate this in one step. For that st pairing, that's going to become 1 minus 4, so x should equal negative 3. For the same st pairing up here, 12 times 1 times negative 1 quantity squared would be a positive 12. Okay? And now that everything is here, you just evaluate this expression for the correct value of the correct variable. Okay? So, in this case, partial of f with respect to s would crunch out as y minus 2 first, so that'll be a 10. Keep in mind that's multiplied by 2s, so it'll be times 2. And then plus x plus 2y is going to be negative 3 plus 24, so that's going to be 21, I believe. I'm terrible at arithmetic. I'll admit it. I suck at arithmetic. I have to have variables. I have to have operations. I have to have that. I stink at arithmetic. So 12t squared is 12 times 1, so it'll be times 12. So you're crunching out 20 plus whatever 12 times 21 is. I'm not a human calculator.
10 plus 42, 252.
252. Yes, you are a human calculator. Plus 20. I guess you can handle those 26 hours you're taking.
Absolutely.
Yeah. So the rate of change of f with respect to s when s is 1 and t equals negative 1 turns out to be this. So an interpretation. The z values of this function, f, are increasing at that rate, 272 z values for every s and t value, 1 unit away from these that you're, going in the st direction. Okay, it's just this, just evaluating this expression. This is another thing that's kind of hard to see. Okay, I mean it's easy to see how it could be used, but it's hard to draw a picture with it because you have the f function which you could draw a picture of, but you're not using a global domain for this function. You're only plugging in x and y values that come from these expressions, and that's also another two-dimensional domain. So there's there's some extra dimensional things going on here that make this not really, lending itself to making a cool picture. But that's what the calculation actually just boils down to. It's just linking all the dependencies together to get that rate of change. So this one, similar idea. The rate of change of f with respect to t. You don't need to see that one? Pretty straightforward. I'll fill it in before I scan it in though, okay? So it works the same way as this, because there's one more thing I want to show you. There's only a couple of things in section 14.6. The idea behind the chain rule, so as long as you've got your branch here, your pyramid, that's all you really need, so you can connect all the pieces together. The other thing is revisiting a topic from Calculus 1. How many of you remember doing implicit differentiation? It's a topic everybody, and you're raising your hand and you're shaking, it makes you nervous. So a little bit, okay, that's what you're doing, so. Implicit differentiation, when you first saw it, was dealing with things like this. It was a way of finding slopes and tangent line slopes on curves that you couldn't solve for y being a function of x. You learn all these rules where it's depending on y being a function of x. Like, y equals cosine x, y prime is negative sine x, and stuff like that.
So we get all the x's on one side and the y's on the other side?
Yeah, something like that. So if you're dealing with something that's implicitly defined, see, this is the equation of a circle, centered at the origin, radius 5. I could solve this for y and turn it into a function, but if I wanted to find the equation of the tangent line, or the slope of the tangent line on a point here, like let's say the point -4, +3, or something like that. Or -3, positive, I think I got that wrong. -4, 3. So let's say we wanted to get the slope of the tangent line to the circle right there. We could solve this for y, bring the x squared over, take a square root, keep the positive square root because you're dealing with the upper half of the circle, then you're committing to a chain rule derivative, and you don't have to do that. The way implicit differentiation worked old school is you take the derivative of every variable, but keep in mind you want y to still depend on x in terms of slope. So when you do the derivative of x, it's still just like always. The derivative of x squared becomes 2x. But tucked inside of y, you want y to still be a function of x, even though it's not really written as a function. So when I do the derivative of y squared, it does give me 2y. But since the quote inner part is to maintain y being the function that depends on x, the chain rule makes you multiply this by what? Do you remember? In implicit differentiation, you multiply this by, some teachers taught to multiply by y prime, some people taught to multiply by this.
Yeah.
So every time you do a derivative of a function on y, you still apply the regular derivative rule. Y squared becomes 2y, cosine of y becomes negative sine y, but if it's a function of y, you immediately multiply by that dy over dx multiple, so that you put the derivative presence in the equation. And then the derivative of 25 is 0. And then you're remembering it. You want to solve this for dy over dx, so you get all the other stuff over here. 2y dy over dx equals negative 2x, and then you divide both sides by 2y. So you get dy over dx equals negative x over y. Okay? And that was probably your first example, something like that you saw. And then the homework and the other examples got a lot messier than that. And then if you had x's and y's written together, you had to do the product rule. If you had x's divided by y's, you had to do the quotient rule. So Calc 1 implicit derivatives are a real mess. But just a quick show of hands, did anybody have Daryl Thomas for Calculus 1?
Yes, sir.
Then you have seen this.
Yeah.
You've seen what I'm about to show you, because I think he actually teaches Calc 1 students the Calc 3 way of doing implicit derivatives. I think. At least I've heard that rumor. I've never actually got it confirmed from Daryl. But you remember doing this?
Yes, sir.
Okay. So, and then if I wanted the slope, I've got the point of tangency. I would plug in negative x. So my tangent line slope, my m, would be positive 4 divided by 3. So that tangent line would have a slope of 4/3. And then we could use the point slope formula to find the equation line and things like that. But you're about to see implicit differentiation taken to its easiest extreme possible. Okay, and it's in this chain rule section 14.6. So, without further delay, if you ever need implicit derivatives again, This will be the ultimate be-all, end-all way of doing implicit derivatives, okay? So you start off, in some cases you start off with a function of 3 variables, or it could be 2 variables. It doesn't have to be a function of 3, okay? Most of the homework problems you see in 14.6 that pair with this are functions of 3 variables, so I want to be consistent. You start off with this relation, and this is implicit. This isn't solved as z depending on x's and y's. It's like the equation of a sphere. It's an implicit relationship between x's, y's, and z's like this that's sort of jumbled up in one equation. But you can still talk about, you know, the rate of change of z with respect to x and z with respect to y, even though it's not from a function. It's from an implicit relationship. So if you start with an implicit curve like this, the implicit derivatives, in other words, the rate of change of z with respect to x, the rate of change of z with respect to y, can be calculated using this calculation using separate partial derivatives. Now this looks like I've mixed my notation up, but if you notice, the way I committed it to memory as a Calc3 student is I just memorized that everything flips. If I want to do partial z with respect to over partial x, partial of z with respect to x, I need to calculate this, the negative quotient of f's partial with x divided by f's partial with z. And if I want to get the partial of z with respect to y, I need to take this f, this original expression from my implicit surface, and do its negative partial with y over partial z. So notice, you know, z over x here flips x over z there. Z over y here for your partial flips y over z. And that's just the way I committed it to memory. So I guess I'm implying I'd like you to know this. Okay? Yes, sir.
The capital F, like on the first one, that's with respect to x over respect to y?
Yeah, this is partial of f. This is another version of the partial derivative notation. So it's this thing's partial with respect to x divided by this same thing's partial with respect to z. And then a negative put in front of it. So I would just start by putting the negative there. So let me do this example because, I mean, this one's, we could probably, you know, look at this on the graph, but I also want to do it for the calculus 1 example because you can also apply it to a function of 2 variables. In other words, you can go back here. Well, hey, let me just go in and show you, since I've already done this. Rename this a capital F. And I guess technically you can bring the 25 over if you want to, and set equal to 0. Either way, it's set equal to a constant. And if I wanted to get, well, in this case, the derivative of y with respect to x. I'm not using partial derivatives here because why? Why am I not using the del symbol?
Because it's only 2.
It's a 2 variable relationship, so I can only talk about Arabic dy over Arabic dx. The only time you need partial derivatives is if, you know, well, 3 or more variables are involved in your implicit relationship, okay? Or you have z depending on more than 1 variable. So that's the main distinction. Has that been pointed out to you? I mean, you're still relatively new to partial derivatives, but that's the whole reason you have this whenever z depends on 2 or more variables, and you go back to the regular good old English dy over dx when you're dealing with a function of 1 variable. And again, this isn't a function, but you're still wanting y rate of change with respect to x to come from a slope where y depends on x. So that's why you're using this here. But it still involves the same calculation. If you wanted to make a parallel between that and this would equal negative f's partial with respect to whom first?
X.
Yeah, keep it in mind it's going to flip. So this would be f's partial with x over f's partial with y. And if I've redefined capital F to be this equation for the circle, set equal to 0, then negative in the front, that partial with respect to x is 2x, divided by that partial with respect to y, 2y. Your 2's cancel. And it's the same thing we got using the Calc 1 method, but a lot easier. Okay.